combination reactions before, and for combination reactions, the only thing that you are making as a product is one compound. And you combine two simple elements or water and an oxide, or with metal oxide or non-metal oxide. So depending on what you had, as reactants, the product was different, but it was still one single product after the yield side. The decomposition reaction is exactly the opposite. Basically, you're taking a compound made of two or more elements or two or more ions, like AB here, and you break it into smaller components. You break down the compound. So you're gonna have one reactant, and then you're gonna have to have more products. Now, depending on what the reactant is, we have different type of decompositions, and what I'm gonna present here are a few of them. It's not an extensive decomposition situation here, but the most important ones, and by recognizing the patterns, depending on what your compound is before the yield sign, it creates a certain pattern of reaction. And that pattern, if you're able to recognize it and apply it, you're gonna be able to do any decomposition that's gonna be thrown at you in the next couple of weeks or so, okay? So, remember the pattern. So the first type of decomposition that we're gonna talk about is the composition of binary compound. What is a binary compound? Made of only two elements, only two, like water. Or we have done magnesium, you made magnesium oxide from reacting magnesium with oxygen, now you can break it. So if you read this reaction from this way, from you flip it over, this turns into a combination. So flipping it, the combination turns into a decomposition. See what I'm saying? Okay. So if I decompose water, decompositions are not easy to come by. You need to help the compound break through, because the compounds that are here are pretty stable. So you need to give them or a shock of electricity, to like water needs electricity to break, or other compounds need heat. The majority have it with application of heat. So you take a compound that is made of two elements, like water, and break it into the elements that is made of hydrogen and oxygen. These are the two elements that make this compound. Hydrogen and oxygen will be your product. But remember that anytime you have to write hydrogen by itself or oxygen by itself, they need the two at the bottom because they are diatomic molecules. They're part of that set of 7 diatomic molecules that I told you that you need to remember, okay? The reaction has been balanced, so no issue with that. So let's do one more on the board. Like, I'm gonna say aluminum sulfide. Aluminum sulfide, remember the charges. Sulfur is a -2, comes here, aluminum is a +3, comes here at the bottom. So if you break this compound, it's a diatomic, it's a binary, it's a binary compound made of two type of elements, aluminum and sulfur. So if you break this, you're gonna get aluminum and sulfur. And in this case, you do not have subscripts because aluminum is not a diatomic molecule, sulfur is not a diatomic molecule. Okay, so just the two formulas of these two elements. So binary compounds breaks into the elements. Okay, now never carry the subscript of the reactants on the side of the product. So if you have 2 and 3 here, that these subscripts do not show up here, but the reaction still has to be balanced. So we have to make up for that through balancing. So I have 2 aluminums here at the bottom, so I'm going to multiply this aluminum by a 2. And I have 3 sulfurs at the bottom, I'm going to multiply sulfur by 3. Good? So that is the situation when you break down binary compounds. Okay, the opposite of the combination. The second type of decomposition that we're going to see is a decomposition of a hydrate. And we work with a hydrate with a copper sulfate pentahydrate. I don't know if you remember it from the lab. So this was A. This was B, a hydrate. And let's say copper sulfate with 5 molecules of water. When you break a hydrate through heating it up, that's why you see here you're gonna see a delta a lot of times, or a temperature. You break it here at the water. You separate the water goes away. It's gonna basically break and evaporate. So you're gonna have copper sulfate as the product and the water. How many molecules of water? Exactly how many you have here, because you have to keep the reaction balanced. So this is one of the simplest type of decomposition, because all you have to do, instead of putting a dot here, on the other side, you put a plus instead of the dot. And you keep the numbers exactly the same, because the reaction has to be balanced. Here you have the situation of nickel 2 sulfate heptahydrate. Take the dot away and replace it with a plus, and you broke this into the components. So the pattern for this reaction is any hydrate breaks into the salt. This is a salt, an ionic compound is called a salt, and the water of hydration. So that's the pattern. Good so far? Okay. The next type of decomposition, so we have a bunch up to G. So the next type of decomposition, C, would be a carbonate. What's a carbonate? Any metal that is combined with the group polyatomic ion carbonate, CO3. CO3 has a -2 charge, and the metal in front can have any charge, +1, +2, +3, plus whatever. So a metal combined with a CO3 with a carbonate creates a metal carbonate, basically, a carbonate. The pattern for the carbonate is, it breaks into the metal oxide, basically the first element is the metal, so you make the oxide, metal combined with oxygen, and by default, CO2. Here you have CO3, do not copy the 3, because you don't have a CO3, here you have a CO2. So that is the pattern of breaking a carbonate. And here you have the calcium carbonate, breaks down, this delta here means heat, temperature, into the metal oxide. Metal is calcium, oxygen makes for the oxide, +2 -2 charges, the charges here cancel, so CaO is your calcium oxide, and CO2 by default, okay? Let's do another example. If I want to decompose sodium carbonate, the formula for sodium carbonate, remember the charges, +1 for sodium, CO3 has a -2, when you cross it over, you get Na2CO3, right? So what is the pattern saying? Any carbonate breaks into the metal oxide and CO2. What's the metal here? Sodium is your metal. So how do you write metal oxide? Sodium oxide is sodium and oxygen. Remember the charges, +1, -2, so you only cross it over, is Na2O. That's your sodium oxide. That's your metal oxide. I'm erasing the charges. Once I cross them, I don't want to see them anymore. And carbon dioxide by default. Okay? That's part of the pattern. So if you understand that the carbonate breaks into the metal oxide and CO2, you can break any carbonate, because it doesn't matter what the first metal is, you always combine it with oxygen and cross the charges to figure out the formula of the oxide. And CO2 just pops in there automatically. Okay? Now, some of these reactions are balanced, like this one I see is balanced. This one was balanced also, but that doesn't mean that all of them are balanced. You have to kind of keep on balancing. But everybody understands how carbonate breaks into. Good? Okay. All right. The next type of decomposition is a chlorate. So we have different type of compounds that break in different ways. If we remember what compound breaks into what, you can actually replicate this and apply to any kind of compound. So chlorate, what's a chlorate? Something that contains the polyatomic ion ClO3. That is your chlorate. So a chlorate breaks into the metal chloride. Metal is always the first element, right? The metal chloride. Chloride means it's metal combined with chlorine, with Cl, right? And oxygen by default, O2 by default, oxygen gas. So you basically break it here before oxygen, but instead of putting O3, you put O2. So let's look at this, KClO3, so for D, we had potassium chlorate. Potassium has a +1, ClO3 has a -1, remember the charges. Breaks into, the rule says, metal chloride, K is your metal, potassium. Potassium with chlorine together, +1 with a -1, the charges cancel, right? So KCl is the formula of the potassium chloride. and O2 by default. Balancing for this, potassium and chlorine are good. Oxygen has you have a 3 and a 2 here. How do you reconcile a 3 and a 2? By going for 6, right? So I'm making 6 oxygens here by multiplying by 3, and I'm gonna go for 6 oxygens on the potassium chloride side by multiplying by 2. That messes up my potassium and chlorine, but I can fix that by multiplying this by 2. Okay? Let's look at another example. Let me erase this now. I want you to decompose aluminum chloride. Aluminum chloride. Okay, so how do you write aluminum chloride? Let me change the color. Aluminum is Al, chloride is ClO3. Okay, now charges. Aluminum has a +3, ClO3 has a -1. So basically I have to cross it over and put a parenthesis and a 3 here. That's your aluminum chloride, okay? When you break this down, the rule says, break it into the metal chloride. The metal is aluminum, the first element. So aluminum followed by Cl, okay, metal chloride. Again, charge is 3 minus 1. The 3 drops here, okay? So aluminum chloride, and what else? By default, O2, oxygen gas. Okay. So these are your products. You can predict the products, and now we have to balance the equation. 1 aluminum, okay, 3 chlorines, okay. You have 3 times 3 is 9 oxygens. 9 oxygens. You can put a 9/2 if that suits you, or remember the rule, when you have an odd number of oxygen and an O2, put the whole number in, and then what you do with the other coefficients? You double them up. 2 and 2. Okay? So that was your chloride, the pattern for chloride. The next is a hydroxide, the next pattern that we're going to talk about. What is a hydroxide? A metal combined with the group OH, the polyatomic ion called hydroxide. So in this case, you have aluminum hydroxide. And the pattern says, any hydroxide breaks into the metal oxide and water. And you have seen this when we combine metal oxide and water to make the hydroxide. You've seen it in the combination of synthesis of metal oxides and water. Okay, so this is the reverse of that. So hydroxide, this was E. This is aluminum hydroxide, breaks into aluminum oxide, Al2O3, so -2 plus 3 charge, you crisscross them, and water by default. And this is all the balancing. So again, metal oxide and water makes the hydroxide, and the hydroxide breaks into metal oxide and water. You've seen this as a combination. The next one is the acids. And remember that we had the non-metal oxide and water. We put them together in such a way that we write in the format of an acid. So when you break it, you're gonna get water. So let me show you how to do this. So this would be F. H2SO3 in this case. You know that you should get water. I'm gonna write water first. Remember when I told you that it doesn't matter which one do you write first. And then you have to write whatever is left after you subtract 2 hydrogens and an oxygen from here. If you take 2 hydrogens and 1 oxygen from this sulfurous acid, you're gonna get SO2. If you subtract -2 hydrogens and oxygen from here, you're gonna see SO2 being left over. Same thing here. Carbonic acid breaks into CO2 and H2O. You can write H2O and then subtract it from H2CO3, and what's left is carbon dioxide. Because remember when we did combination, we put them together to make them look like an acid. Okay? Alright, so that is your acids. And carbonic acid, every time you open a soda, you're gonna see those bubbles coming up. That is your carbonic acid decomposing into the carbon dioxide, the fizz, and the liquid that is in there, which is the water base. Okay? And every time you take a drink of water and you blow, you breathe into your water, you actually make carbonic acid, H2CO3. because carbon dioxide and water react together to make this, and this also breaks into carbon dioxide and water. So one is combination, and the other way is decomposition. Good? Okay. And the last type of decomposition that we're gonna consider is just to kind of, to just remember this. Normally when you have binary compounds, that's how we started the decomposition. When you have binary compounds, you break them into the elements. And I told you that water, for example, like water broke into hydrogen and oxygen, right? Because it's binary, made of two elements. But there is a category of binary compounds that are called peroxide, made with a polyatomic ion, O2, with a -2 charge. This is a superoxide, so the peroxide is the one that we put on wounds, okay? The peroxide is a supercharged oxide, basically, with more oxygen in it. This, because it has this peroxide group in it, breaks into the water and oxygen gas. When you put it on your skin, it's gonna make that little fizz. That's your oxygen that comes out, and that's the disinfectant that is in the peroxide, actually. So a peroxide, H2O2, breaks into H2O and O2. So it's a little bit different reaction. These are binary compounds. This is also a binary compound, but it's a special category. That's why I wanted to put it in here, just to kind of, for you to kind of remember that. So the only peroxide that you're gonna be asked about at this level is the hydrogen peroxide. There are other peroxides, there's sodium peroxide, different metals with the group peroxide, but the only one that you need to be worried about is the hydrogen peroxide, because the rule says make it into the oxide. Water, it's hydrogen oxide, basically, if you think about it, and oxygen gas. So water in this case is oxygen. Remember this reaction just as is, because you're gonna be, if you have to face it, you know where it comes from, okay? All right, so these were all the type of decomposition reactions. Remember, some of the decomposition, if you flip them, you actually get to the combination reaction that we talked about, okay? So remember the patterns of reactions, maybe write them down on a paper, and that's how you remember exactly, you can figure out whatever I throw at you from these categories, you're gonna be able to solve it. Good? All right.